Physics Bites,
Physics Bites,
a science podcast in English by the students of Notre Dame d'Ascension.
Hello and welcome to a new episode of Physics Bites, the English language physics podcast of the students of Notre Dame d'Ascension here in Paris. So we have a new episode with our senior students. They're going to talk to us about nuclear energy, what there is on the horizon coming in terms of civil nuclear energy, maybe fusion, but we'll get into the details. So I'll let them introduce themselves.
Hello, my name is Lily.
We have Lily here, who's been a student of mine for 2 years now. And?
Hi, my name is Marion.
And Marion, who has also been a student of mine for 2 years. So Marion, you've been doing physics as your major topic this year. But Lily, you stopped after grade 10,
yes.
Right? But that didn't stop you from doing physics in English for the last 2 years. All right, so let's get right into it as quickly as we can. I'll let you guys maybe give us a short summary of what you talked about in your presentation, and then we'll dive into some details, okay? So.
I think, first of all, it's important to remind everyone what is nuclear fission. Mm-hmm. So nuclear fission is when you have heavy atoms. Mm-hmm. Generally, it's uranium-235, right. Which is...
But not only uranium-235, but mainly.
Mainly. Mm-hmm. And we send a lot of gamma rays, I think. If I remember correctly.
When a neutron hits the nucleus of this heavy atom, it splits
in two, and it creates energy, mm-hmm. which is nuclear energy. So that's the fission part. Well, right. The other one is fusion. We did not mastered it today.
You didn't talk about it too much, and even technologically speaking, you mentioned that we haven't gone further than mostly theory and some prototypes that we're working on, even though we recently had some news about it. Maybe we'll come back to it at the very end, yeah?
And fusion is the opposite of fission. It's mm-hmm. when two atoms become one, which also creates energy.
Right. So while we're still on the theoretical side of things, maybe Marion, you can tell us, where does this energy come from? Why is it that when we have fission or fusion, there's lots of energy, a huge amount of energy is released? Where is that energy coming from?
This energy is coming from the fact that there is, there is bonds,
right,
between inside of the nucleus to keep all of the protons and neutrons together. Yeah. There is a force that is called the strong force, right, or a strong nuclear force,
right,
and it glues them together. And when a neutron hits that nucleus, it breaks that
bond
between them, and that's where the energy comes from.
Right. So this energy is from what we call a form of binding energy, and this binding energy binds the nucleus together. And it's a very powerful force because, as we studied in grade 10, protons are all positively charged, so they want to move away from each other with a very, very intense force. So if something is going to keep this thing together, it has to be even stronger. That's why we call it the strong nuclear force. There's another way of also interpreting this energy that is coming from something that maybe you guys came across called missing mass. And this goes back to Einstein's famous equation. No?
Not me, but maybe Mark.
the more physics oriented.
Yeah, because energy is closely linked to the mass.
Right. This is a famous equation from Einstein, E equals mc squared. So if we have the mass of something, if we multiply by the square of the speed of light, that gives us the equivalent amount of energy. Well, let's talk about fission to begin with, yeah? So when you have a uranium atom.
You have a uranium atom. You split it in two. There is energy released because...
So if we compare the mass of the uranium atom before splitting, and we compare it to the mass of the particles that come out after we have split it...
Yes, there is... the two particles that come out are... less heavy.
Right, like the sum of their masses doesn't add up to the mass of the original uranium atom. And there's a very slight difference.
Yes, and that slight difference is the energy that has been produced.
Right. So one way of interpreting this is to say that missing mass has been converted into energy, and that's where that energy is coming from. Another way of thinking about it is, as you said, is that the way the nucleus is held together with that glue, this binding force, when we break that bond, well, it kind of releases that energy the same way that a chemical bond is releasing energy when, for example, we burn some sort of a combustible something. Okay, so that was fusion, and the same thing happens with fusion, right? So when they go together, the mass of the new heavier particle is less slightly than the mass of the component atoms that came together. Okay, so that's the principle behind it. So when we talk about nuclear energy, this is that energy. You guys went on from there to talk about a lot of nuclear civil uses. What do we mean by civil nuclear energy usually?
Well, there is...
Maybe you can give us also a bit of a history of all this.
So the first use of nuclear energy was, it was developed for the army initially, for the atomic bomb.
Right, this is the famous...
Manhattan Project.
Right, 1939 to 1945.
And then we realized we could use it to produce electricity, which is the main use in the civil sector.
Right.
And so we produce electricity through what we call a nuclear power plant.
Right.
In 3 steps.
Okay. So just to be clear, the main thing we're using here is the energy that's being released.
Yeah.
What is the main difference? Let's just begin with the global picture. Is there something fundamentally different between what happens with a nuclear bomb and what happens in a nuclear power plant? Or is it kind of the same thing, but...
Well, in nuclear fission, in a nuclear power plant, it is very controlled.
Okay.
And because when the neutron hits the nucleus, chain reaction.
A chain reaction, yeah.
Starts. And in a nuclear power plant, it is controlled because we do not want it to produce too much energy at the same time. Whereas in a bomb, for example, in the
any
weapon,
kind of a nuclear weapon.
The goal of the weapon is to take that energy, that very big energy that comes from this chain reaction, and to release it
all at the same time.
Yes.
Right. So what you're saying is that fundamentally speaking, the fission in a nuclear power plant is the same as the fission in a bomb. But in one case, we just let it go out of control, and in the other case, we kind of control it. Okay. How do we control it? How does a nuclear power plant differ then from a nuclear bomb?
We control it by the matter we install into the reactor. So we control the quantity, the uranium's quantity we put into it, and when there's no more matter to disappear, the chain reaction stop naturally. Or we can also change the temperature inside the reactor, which change the environment inside it, and I think, if I remember correctly, the nucleus will decrease in speed and it will stop.
You talked about a chain reaction.
Yes.
What is a chain reaction? What is the link between the idea of a chain reaction and what we do in a nuclear fission reaction?
Well, a chain reaction is a reaction that can self-sustain itself, and when it started, in a nuclear power plant, for example, in nuclear fission, for example, when a neutron hits an atom of uranium, for example, it splits, but it produces more atoms that will go and hit other atoms of uranium.
Right. So let's just be clear about this. We have a uranium atom, a neutron hits it, the uranium atom splits into 2 smaller atoms, and also there are
up to 2 to 3 neutrons that are released.
And they're released with a lot of energy.
Yes.
They're very high energy. And what's going to happen with these 3 neutrons?
They are going to scatter around, and each other.
Right. And when they hit the other uranium atoms, those ones are going to probably split because these are very high energy neutrons. And when they each split, they're going to produce 2 to 3 neutrons. So that makes it 6 to 9. And then they're going to hit more atoms. And that's what we call a sort of chain reaction. And it's an exponential chain reaction, right? That's what happens in a bomb. What is it different when we do this in a nuclear power plant? And how do we manage to do it differently?
Well, in the nuclear power plant, the neutrons that are released are slowed down.
How do we do that?
There is many ways of doing it. The most extreme one is we have control rods inside, because the uranium is put inside of tubes.
Right,
and,
which we call pencils, right?
Yes, yes. And in the middle of those pencils, we have other tubes that are called controlled rods. And when we can level them down or up, depending on what we want to do. But if they are down, the neutrons are being absorbed into it. And it's kind of the same thing for the other way. I mean, in a nuclear power plant, we used other materials to slow them down, and I'm not sure, but I think water too.
Right, and water is one of the main ones, right? So if we see pictures of what it looks like inside a power plant, you usually see this giant pool, which is called a pool, where you have these rods with the nuclear fuel, and that's where the reaction is taking place, so that when the neutrons are being expulsed, they can, going through the water, they can be slowed down and they won't get out of control. Sometimes it's called heavy water.
Yeah, which is when it's enriched with more isotopes of...
Right. Which isotope of hydrogen in particular, do you remember?
Deuterium and
Right, so it's a water molecule, but the hydrogen atom in the molecule is a heavier kind of hydrogen, right? A heavier isotope of hydrogen, as we say. Okay. So go on, explaining the rest of how we produce energy now. And now that we know how the fission takes place in the nuclear reactor, in the power plant, what happens? Fission is taking place. So you said we absorb some of the extra neutrons. So instead of having going 1 to 3 to 9 to 27 and so on, we absorb half of them. And so we still have a reaction that's a chain reaction, but it's not exponentially growing. So one atom is going to hit another atom, which is going to hit another atom, and so forth. So that allows us to control the reaction. What happens there? How do we get from there to electricity?
So when we release nuclear energy, it starts to create heat that we transfer into near turbines, which start to move. So we convert heat to moving electricity, to moving energy.
Right,
sorry.
Kinetic energy.
Okay. And then we... there's a generator next to the turbines, which change the mechanical energy into electricity.
Electrical energy.
And then we put them on the civil networks.
Okay, and that's where you guys talked about the different types of nuclear power plants which we can have, because so the idea is simple. Fission releases energy usually in the form of heat. That's going to heat up water. Water is going to turn into steam with high pressure. It's going to turn a turbine. Turbine is going to be connected to an alternator, to a dynamo, which is going to produce electricity. Why is it that we have different types of nuclear power plants? We talked about first generation, second generation, third, fourth, fifth generation, which haven't been built yet. Why are some better? Why do we want to change things? So now we're getting into much more the engineering side of things, right? So much more the technical side. What are the different types of nuclear power plant we have? What are the differences, and why would that make a difference or not?
So there is many types of reactor, as you said, because all of them are not using the same components or techniques, because it's always the same base with nuclear fission, but we have the most common power plants, which is water-cooled power plants. There is a simpler version where there is not a secondary circuit for the water.
Right. So let's see what that means. You talked about, so if I'm looking at my notes correctly, you talked about a few of the most common types of reactors we have. You talked about boiling water reactors, the BWRs, pressure water reactors, the PWRs. You talked about fast neutron reactors, molten salt reactors. Now, which ones are the most common that we have in the world?
The first one, the pressurized
The
water.
pressurized water, right? And then boiling water, and then do we have any fast neutron reactors that are functioning in the world today?
No.
No. We used to have one, which was in France.
Yeah.
We had two, actually. One was called Phoenix, and the other one was called the Super Phoenix. But the Super Phoenix was the only one that was connected actually to the grid. And it was shut down in 2012, which is the only one working. But the technology comes back from 1960s. And then the molten salt reactors are kind of like fast neutron reactors with some differences, right?
Yeah, but they use molten salts to cool down.
Okay. So let's go to the most common ones, the pressurized water and the boiling water. You talked about secondary circuits. What are we talking about here? What is a first primary circuit? What is a secondary circuit?
So the primary circuit is when the energy is released.
Right. So now that where we have the fuel, the nuclear fuel. Okay.
So that's the heart of the nuclear power plant, and then we have the secondary circuit, which is used to cool down with water, for the most common one.
Okay.
To cool down the reactor.
Okay. So are you sure it's for cooling down the reactor, or is it for...
No,
I think Marion is not agreeing with you on this one.
Yeah, the primary circuits contain water that is directly in contact with the core. And
which is where the radioactive material is.
Yes.
Okay.
And the secondary circuits also contains water, but that is where the steam is produced for the turbine. That way the water that is contaminated by the core is not in direct contact.
Right.
With the rest.
Because the water that's in contact directly with the nuclear fuel will contain some radioactive waste materials.
Yes.
And so we add a secondary circuit in order to have water which remains quote unquote clean.
Yes.
And then we transfer the heat from the primary circuit to the secondary one. And this is which kind of reactor that is like this?
The pressurized water.
Which is the most common one, right? Do we have boiling water reactors still working today in the world?
I'm not sure.
I think in your presentation you mentioned something like 1/5 of the power plants are still like that. Okay. Any advantages to the boiling water reactor?
22%.
22%. There we go. I thought I remembered some number from there.
It's simpler because there is not the secondary circuits, but
so cheaper to build as well.
Yes, but yes, the water has to be decontaminated further.
Right. And if there is a leak of the water, then it's less safe.
Yeah.
Okay. So it's reassuring that the most common type of a power plant is a safer kind we have today. You talked about heavy water reactors.
Yes.
Do you want to tell us a little? I didn't know about that one. Can you tell us what we mean? What is the case of heavy water reactors?
Heavy water reactors contains water that is not natural. As I said, it contains isotopes of hydrogen, and uranium 235 has to be enriched.
Right, we didn't talk about enrichment.
Yes. Well, it comes from the uranium that we collect has to go through a process called enrichment in order to be used in a nuclear power plant. And with heavy water...
what is enrichment? Why do we need to do this process?
Enrichment is a process where you take the uranium and you put it in...
These centrifuges.
Yes.
Right.
And other things in order to
So let's go back to the basics, right? If I go to a country which produces uranium, like Kazakhstan or Australia or somewhere like this, where there's a lot of natural uranium, and I go to a uranium mine and I take out 1 kilogram of uranium, and I look at the different atoms that are in there, what would I find? Which isotope of uranium is most common?
238.
Right. And 238 is good, but for fission reactions, it's not the ideal form.
Yes.
Which one is the ideal isotope?
235.
Right. And what percentage of my 1 kilogram of uranium that I find naturally in a mine contains the right kind, the 235? You remember?
0.03%, I think.
A bit more. It's about 0.7%, right? So out of 1 kilogram, it would be 7 grams.
Yeah.
Okay? In order to be able to use this uranium in a nuclear power plant, what has to be the percentage of uranium-235?
More than 50?
Much less than that. Otherwise, we'll be in trouble.
I don't know.
It's about 3.5 to 5.5%, right? This is what we call enrichment levels for civil nuclear energy. If we want to make a bomb, it has to be above 80%, right? What we use in hospitals for nuclear medicine that your classmates talked about when we were talking about biophysics, it's about 20%, right? So in order to get from 0.7 to at least 3.5 or to 4.5 and 5.5, we need to increase the percentage of uranium-235. We have to enrich the uranium naturally until we reach that level, right? That's what we do enrichment for, so that we can have the proper isotope, which is the one we use actually for our power plants. Okay. And then you said that the heavy water ones don't actually require enriched uranium.
Well,
at least that's what I had from your presentation.
yes. But actually, maybe you could talk
She's
about
passing
that.
the buck on to Lily. So you said we talked about pressure water reactors, boiling water, which are basically all the reactors that we have in the world today. And there are plans for fast neutron reactors and molten salt reactors, but we haven't made any. But what are the advantages of a fast neutron reactor? What is the difference between the other ones, and what is the advantage or the advantages?
Yes. So fast neutrons reactor were developed in the 60s, and as you said, it uses the fast neutrons that are produced in nuclear fission, and they are not slowed down.
Right. So we don't control them like we do with the power plants that we have. Okay.
So they are moving at about 20,000 kilometers per second.
Right. Very high.
Yeah. Whereas in a thermal reactor, a normal one, it moves at about 2 kilometers per second. So they are very, very fast.
So they have lots of energy.
Yes. And so when they eat... in those reactors, you do not need necessarily to have uranium-235, and you can use uranium-238.
Mm-hmm. So that's one advantage. We need the enrichment much less vitally. Okay.
Yes. So.
And another advantage?
There is less waste. So
almost no waste if it's done right, because the waste that we have is what is it that we call nuclear waste? There's two things, right?
It's the materials and all of that are contaminated.
Right. So basically, what is the result of fission?
Yes.
With like krypton, barium, cesium, all these things, but also the uranium-238, which hasn't been enriched.
Yes.
So actually, about 95% of the nuclear fuel is not used when we use the pressure water, because only the enriched part is used. Here you're saying that the whole thing can be used.
Yes.
So for the same amount of uranium, we produce much more energy, and we don't have any nuclear waste left over behind. That sounds pretty good to me. Why do we not have fast neutron reactors everywhere?
As I said, it was developed in the 60s, and there was a project in France.
Mm-hmm. And it was working for many years.
Yes.
But
I'm pretty sure it's... it's...
like most problems we have in terms of nuclear construction is it's very technically complex.
Yeah, and we lose. We have lost many of our nuclear knowledge over the years because, we took the thermal reactor, the normal one, and we said, "Oh, that works," and we didn't keep the
research, I guess.
Yes. And even the engineers that did that, they were not replaced.
Right.
So it's much harder to do, and now we kind of have to redo all of our research for it. Right. So
it is a technically difficult thing to do, just because we don't use water as the sort of controlling agent in there. There are other things that we have to use which have other difficulties. Maybe we can link it to molten salt reactors because they are very similar to fast neutron reactors, and they also have the same sort of difficulties because of primary circuit containing salt, secondary circuit containing water, and if there's the slightest bit of leakage or contact, can be dangerous. So do you want to maybe quickly go over what we mean by molten salt reactors and how much of the two types kind of are the same thing?
So molten salt reactors, as you said, are reactors that are not cooled down by water, but rather by salts, because the fissile material is dissolved in it.
Right. Just to be sure, we're not talking about salt that we put in our food.
No,
we're
it's
talking
liquid salt.
Right, and salt is a whole category of chemical molecules, of which table salt is one kind.
Yeah, there is sodium, there is...
Right. They're generally electrolytic compounds which contain an alkaline ion and, halogen or something of that sort. Okay.
Yes.
I think technically the definition of a salt is the result of a reaction between an acid and a base, if I remember correctly from the old days.
It's very complex because we have to also test for multiple salt chemistries, which one is the better. But
what are the advantages of it? Why put the research and time into this? What can be better about molten salt reactors? Do you remember?
Because I think it.
I think part of it is because the molten salt is a better carrier of heat, so it's much more efficient in terms of the amount of energy that it captures that we can use to produce electricity. And also because you can do fast neutron reactions in molten salts. It captures the heat and it controls at the same time, so there are many advantages that go to this. Okay. You also talked very briefly about some newer generation nuclear fissile energy, like fourth and fifth generation ones using thorium and all these things. Do you want to maybe give a slight overview?
It is still in research, but we could use thorium as a fuel because it's there is kind of like uranium 238, there is more of it.
So just to compare the two, thorium is an element that's found naturally.
Yes.
It's element number 90, I think, if I'm not mistaken, whereas uranium is 92. It also has radioactive isotopes, but it is much less radioactive than uranium. But like you're saying, there's much more thorium on Earth than uranium.
Yes, and in itself, it's not a nuclear fuel, but it can be used to create one.
Right. Through a bunch of nuclear transformations, we can turn it into...
you can form uranium-233, which is...
also good fissile material. Okay. We don't have any thorium reactors working today? Not commercially, at least.
No, not commercially. But I think there's probably a lot of research. So
I think China and maybe India, if I'm not mistaken, but I'm sure that China has put a lot of research into it, and they're ahead of most Western countries when it comes to research into thorium fuel cycles. Okay. Well, maybe we can move on to one of the problems of nuclear energy, the main problem of nuclear energy, which is nuclear waste, right? This is what scares people. This is what everybody thinks of first when you talk about nuclear energy. Instead of thinking of clean, carbon-free energy, abundant, people think about nuclear waste. So this problem of nuclear waste is one of the main communication, I guess, or propaganda problems we have with nuclear energy. It's what scares people. It's what politicians bring up when they're against nuclear energy. Maybe we can go into some detail what the problem is. Why is it such a polemical topic? What the solutions are? Is it as bad as people make it out to be? Let's go into that. Lily, do you want to maybe talk about it a bit?
Yes. So first of all, there's 3 types of nuclear waste. There's 3 types of nuclear waste. The first one is low-level waste. So there represents the majority, I think 90% of the waste created after we use the fuel, and it needs no infrastructure to.
So low level of what? The waste we're talking about?
Radioactivity in the waste.
Can we just, before we go on, what do we mean by radioactivity? Why is it good or bad, or?
Radioactivity is still nuclear energy which is emitted by contaminants.
No, but any isotope which is unstable can become radioactive.
Yes. When a nucleus is unstable, it will do anything to become stable again,
right.
And that means losing a part of its energy,
right.
By emitting a form of radiation.
Right. And basically, we have 3 main forms of radiation. Do you remember what they are?
We have alpha, beta, plus and minus,
right,
and gamma.
Okay, and very briefly, what is alpha radiation?
Alpha radiation is the emission of
It's the emission of the equivalent of the nucleus of a helium atom.
Yes.
So 2 protons and 2 neutrons. That's what uranium usually naturally does. If you take, that 1 kilogram of uranium, it's giving off tons of alpha radiation just because uranium, even 238 or 39 or 37, 4, 5, 6, any of these are not very stable. So they're constantly giving off these alpha particles, and that's what we would call the radioactivity of this. Beta particles are slightly different.
Yes, it's the emission of an electron.
Right, or in the case of the beta plus...
a positron,
right.
Positively charged electron.
Right, which is also what we call the antiparticle partner of the electron. And then there's gamma radiation, which is considered the most dangerous and the most high energy one. And what is that?
Well, it's the emission of a proton.
No, there's no... So if you want to associate a particle to it, is a photon.
Oui, c'est un photon. Oui,
in English. So it's basically high energy electromagnetic radiation. Okay, very high energy. Okay, and the most dangerous of this is gamma radiation because it can penetrate almost any depth, whereas that 1 kilogram of uranium, if I hold it in my hand, it's not going to do any harm because my skin is basically going to block all of it, right? Beta radiations generally are a bit more dangerous. They're more high energy, and gamma is the highest energy one. Okay. What is the danger from radioactivity? Why do we need to classify the nuclear waste? Why do we have to control it and all these things before we get into details? Where's the danger? Why is that
it
bad?
can impact negatively our health, so it can create cancer and even cardiovascular disease.
Right, it can even kill us within a few minutes or hours. Why? How does it do this?
Because it destroys the DNA.
Right. It can create mutations in a DNA, which can have negative consequences, or it's just so powerful that it can destroy tissue, right? We kind of use that in nuclear medicine to kill bad tissue, cancerous tissues, right? Okay, so, and what is most dangerous about radioactive material? How is it most harmful for humans? If like there's the radioactive material on my hands, is it dangerous?
It is, but not as much as as it would be if it directly come across yourself, like inside of you. Like.
Right, if it entered the body,
yes.
Right? Because our skin actually is a pretty good protection against a lot of natural radioactivity, right? The world is radioactive.
Yes.
Ground, most of the stones and rocks that we have some radioactive properties. There's lots of materials which are radioactive. We're bathed in radioactivity, but our skin does most of the protection. The problem is that when it goes inside the body, there's no more of this protection, and that's where the dangers come from. It can directly have a negative influence on a genetic level. So you were going to tell us that there's 3 degrees of danger basically associated to nuclear waste.
Yes.
First level, which is low level, and we're talking about low level of radioactivity that's produced.
Yes.
Okay.
Then there's the intermediate level, so it's intermediate radioactivity. So it needs a little infrastructure to protect, to stop the radiation to come out. And then there's the high level waste. So there's the one really dangerous, which emits a lot of radioactivity, and I think it accounts even for 95% of the radioactivity emitted by waste.
Right. So it's important because you gave us a very interesting bit of information that for most of the actual waste is low level, but most of the actual radiation is from the high level, even though it constitutes a very small portion.
Yes.
So like 1 or 2% of nuclear waste emits 90% of the nuclear radioactive energy there. Okay. The good news is that the more radioactive something is, the lower its lifetime, the shorter its lifetime,
yes.
Right?
And in France, at least, we started to develop a project which is led by the CGO program, and Marion worked on it.
Yes, the CGO project is the Centre Industriel de Stockage Géologique pour les Déchets. It's located in Haute-Marne, and it is a disposal facility that will contain all of our nuclear waste, and mainly the high-level waste.
Right.
That will be mainly it's spent fuel or the reactor core. So it will be put into barrels and sealed away. And I think that's why it's controversial, because even if it's very radioactive, uranium has a very even if its half-life is kind of short, it still is radioactive for many centuries.
Right.
And it's still a danger for us and the environment. So many people are scared that we are going to forget that it's there, or that even it will
and the dangers,
the soil.
Right, that's the fear, is that if it's not properly contained, it could contaminate soil and water, and get into our food systems, and then that is what could be potentially very, very dangerous, right? There are different approaches to managing nuclear waste, right? So, for example, Americans, their approach is very, we have to take spent fuel and we have to store it in the most deep, faraway place. In France, we're one of the few countries where we don't necessarily just store spent fuel. We also do other things with it, right?
We recycle it.
Right.
So we take the spent fuel and we add to it what we call a mixed oxide,
right?
MOX.
A MOX, yeah.
And we can reuse it to put it again into a nuclear power plant to recreate energy.
Right, and the advantage of that is twofold, because on the one hand, we need to buy new fuel from countries which produce it, and secondly, we produce less waste. But it is technically
difficult and challenging.
Right.
Yeah, but since the 60s, we have produced enough fuel to power the French fleet for 14 years.
Yeah.
So it's very promising, and many reactors are using this. And there is even a project for the fast neutron reactor to only use MOX fuel. That could be a big improvement.
And if we get to that point, mixing the idea of using, on the one hand, this recycled fuel, on the other hand, fast neutron reactors, it basically means we have fuel that will last us for a very long time, and we produce almost no waste in the end. That would be good. Very good, very good. I think the other point that I wanted to bring up, have we? So, let's talk about nuclear dangers and nuclear accidents. Is nuclear energy as catastrophically dangerous as we think it is, in the general opinion?
Nuclear physics is a really hot topic, especially in politics.
Yeah.
But there's strict rules, and the new generation of nuclear power plants have even more safety infrastructures and facilities into it. And I think what created that fear was the Chernobyl accident. And then the Fukushima accident. Right.
But even when it comes to Chernobyl and Fukushima, there's a lot of things that people think are true, which aren't necessarily as true as we think they are. So let's take the case of Chernobyl, which was an absolute catastrophe, right? So you guys were too young for that. I was a little kid. But can the problem that we saw with Chernobyl actually be a real risk today with the nuclear power plants that we have?
No, not really, because the Chernobyl accidents came from a lot of different factors.
Right.
It was, in a generation of power plant that did not have all of the safety mechanism that we have today.
Right.
And there was a lot of miscommunication between teams. They were short-staffed, and it was a lot of elements that lead to this catastrophe. But today, with the safety measures that we have and the safety mechanism put in place, I don't think it's possible to redo such an accident.
Right. So we can always say anything is possible, but as you say, the reactor in Chernobyl was a very old model, and it wasn't even using heavy water or cobalt or any of these things. It was using graphite as controllers. None of the secondary, tertiary security systems. So while it might be possible to have something like this today, the probability would be very, very low, right? We have so much strict guides and rigorous norms that it's one of the things that makes nuclear energy so costly, right? Because we are so strict about security. That's why it has trouble maybe competing with some other forms of energy. We produce a lot of pollution, but which are cheaper. How much nuclear waste do we produce? A lot? Have we produced a lot of nuclear waste for the last 7 years?
Depends on what radioactivity level you're talking about.
In general, even if we let's take the most dangerous part. Have we produced a lot of nuclear waste? No. I think one of the things that's interesting is that nuclear energy is considered very dense energetically. So for 1 kilogram of uranium, we produce a huge amount of energy, which means that we produce much less waste as well. Most of the space, I think, that's taken up with nuclear waste management is the containers. It's not the actual nuclear waste, right? I remember reading somewhere that if we consider the amount of energy that you need for an adult human for living 70 years, all coming from nuclear energy, the amount of waste that it would produce would be the equivalent of a Coke can.
Yeah, approximately.
So which means that all the nuclear waste that we've produced since the 1960s is, you can fit it in our school, barely half the school.
Yeah,
right?
That's why a big nuclear nation such as France only need one facility for storing waste.
And it is completely carbon free, right? There's no carbon emitted except during the construction of our plants. And they can last a good 50, 60 years at least.
Yes, and there is projects to even add more time to that.
Right, to prolong the lifetime of our nuclear power plants. Like you said, we have a lot of science and technology around nuclear energy in France. It was one of our strong points. We've slowly lost it over the years, but if I'm not mistaken, Marion, your goal is to go into engineering in order to become a nuclear engineer. Is that it? So nuclear energy holds a special place for you in your heart. Very good, very good. Maybe we can very briefly talk about fusion? Or no?
Yes, of course.
Unless you guys have any particular topics that you wanted to bring up, maybe, that we didn't manage to cover.
No, I don't think so.
I think we did a good job of going over everything. So let's go very quickly over the idea of what nuclear fusion is, where we're at with that. And then maybe we can talk about the interesting bit of news we had a couple of weeks ago.
Yeah.
Okay, Marion.
So nuclear fission, as Lily explained, is an alternative to produce a lot of energy with...
It's okay.
With even less waste than we do currently. But in order to have nuclear fusion, the matter has to be in a very particular state,
right?
Called plasma.
So before we talk about plasma, what is the fuel for nuclear fusion? Is it uranium? Is it radioactive materials or something else?
No, it's mainly hydrogen isotopes.
Right, so mainly hydrogen, deuterium, and tritium. And what would be the waste, quote unquote, of nuclear fusion? What would be the resulting, what comes out of the nuclear fusion power plant as waste?
Well...
so the hydrogens are going to fuse together, produce helium. And helium, is it dangerous?
No.
No, it's what we put in balloons for kids' birthdays, right? So helium in and of itself is not very dangerous. It's an inert noble gas. But, as the joke goes, for the last 60 years, we're 30 years away from nuclear fusion. Why is it so difficult?
It is very difficult because in order to achieve fusion, there is dense... temperature and a density needed that is very difficult to achieve on Earth.
Right.
Naturally,
why are you mentioning Earth? Why is it possible outside of Earth?
It's a phenomenon that happens in stars. Actually,
right. It's how stars produce energy.
Yes. In the sun, well, it's a bit different because it's not hydrogen isotopes that are used, but mainly hydrogen chains.
What temperatures are required in a star to produce a fusion reaction?
Yeah, so in a star, because of its gravity
right.
and I didn't explain plasma.
We'll get to it.
So it's very dense and there are very high temperatures, around 15 million Kelvin.
Right, it can go from 4 to like 10, 15, depending on the size of the star. And the combination of this very high temperatures and really, really high pressures puts matter in a plasma state.
Yes.
And the particularity?
So plasma is... kind of a big soup of elements when the particles are detached.
Right. So electrons don't belong to any one atom, and everything is just floating together. Nuclei and electrons, and there's lots of energy. And okay.
So it's easier for those particles to come into contact and to fuse.
Right, especially the nuclear. The nuclei of these atoms, because there's no more electrons there sort of shielding it with their electromagnetic interactions. Okay. On Earth, can we do that?
Naturally, no, but we have invented devices to first put matter into a plasma state and keeping it in that state, because it's very difficult. We have to confine it. So we have multiple technologies for that. The main one is tokamak, or stellarator.
Right. Which are grouped together under the term of magnetic
confinement.
Right. Because maybe if we have time, we'll talk about also inertial confinement, which is done with lasers, but we're running very late. We're already at 50 minutes. So just give us a brief idea of what a tokamak is and how does it work and why is it so difficult?
So a tokamak is a donut shape.
Yeah,
so
torus.
Devices that uses a magnetic field and the current that is going in the plasma to confine it. And the stellarator is basically the same, but it uses less magnetic field because of its complex structure.
Right. The shape of the magnetic field that produces is such that it doesn't require the same intensity, but it's just as difficult to maintain, right? So you talked about maintaining the magnetic field. Why do we need to maintain a magnetic field?
Because we need to maintain the density, the pressure of...
And the temperature of that plasma, right? If I'm not mistaken, I think because we cannot create as high pressure on Earth as you do in the sun, we have to have higher temperatures.
Yes, basically, in order for to have a plasma on Earth, it's much reach approximately 100 to 150 million kelvins,
right?
Whereas the sun is at 15 million.
15, 10, or
so that's almost like 10 times what is
right.
needed.
That is much higher because we can't produce those high pressures, and but we can produce temperatures of that order, and we can produce plasma that we maintain in these magnetic tokamaks, or this magnetic field created by the tokamaks. Where's the problem then? Why are we not producing energy from fusion?
Because in order to produce energy, it has to be in a very stable and it's very hard, and we currently cannot do it.
Because the plasma is at such high energies, even the slightest disruption in the magnetic field or lack of symmetry can completely destabilize it. And so what is the big news that we heard about last week during the holidays?
France broke the time record for maintaining plasma. It was previously held by China. So the waste reactor of the
which is the French equivalent of the Atomic Energy Commission in France here.
Maintain plasma for 22 minutes.
Where was this done?
In Cadarache.
Right, which is where the international program to build the first fusion power plant has been since 2004, which is called ITER, or ITER, as we would say it, I guess, in English. So we were able to hold this plasma at 150 million degrees, I think, for close to 22 minutes, which is quite impressive. It is a very, very, very difficult task. It would be interesting to know how they managed it, but we're getting there slowly, right? That 30-year limit is getting closer and closer. Okay. I think we've talked about pretty much most of the topics. I think we could go on for another few hours talking about waste and new power plants. I think Marion agrees with me, maybe more than Lily, that it's a very interesting and passionate topic. but we're going to stop there. Maybe any final comments? What did you guys find interesting about your research, what you found, what you learned? Was there anything in particular that really left its mark on you, or
I
Lily?
think for someone I don't do physics, so for me it was really interesting to discover how, in France at least, the main part of our electricity is produced, but also to learn that maybe nuclear energy is not as dangerous as it seems to be. And I think we've
converted one person.
Yes,
I think
it's one thing who might have impressed me the most, and I think I would prefer now an energy mix of nuclear energy and renewable energy.
In any ways, we can talk about the question of energy another time, but it is, maybe we can agree at some point that it's not the ultimate form of energy, but we can't transition to all renewables without nuclear, I think. And Marion, you who has had much more knowledge of this beforehand, did you find anything new that was particularly interesting, or did it confirm that you're making the right choice?
Yeah, for me, nuclear energy is definitely a good solution, and France should persevere in that direction. And I think what was interesting in my research was the fusion technologies that are being developed, because even though it's not there yet, obviously, it could be really a very, very good alternative, and maybe more long-term than fission.
That could potentially be the long-term solution, maybe even someday.
With all of the breakthroughs in research in France, I think is one of the pioneers of that, and I think it's very interesting.
Okay, and maybe one final question specifically for you: how do you plan on becoming a nuclear engineer? Have you charted the path? What you'd have to do for your studies?
I will go into class prépa, and I will follow up with.
Are there specific schools that you have found that would allow you to specialize in that as quickly as possible?
Yeah, well, obviously, the best one is, the most renowned is Polytechnique.
Right.
But there is many schools or universities that allows you to take a qualification in nuclear energy.
And how many years would that take?
Technically, it can range from 3 if you want to become a technician to 5 if you want to become an engineer. But I think I'm going to pursue a doctorate, so maybe more. So
potentially going into research in that field and not just an engineer working at a plant or a technician. Okay. I think we had a trip with the students 3 years ago to a nuclear power plant in the north of France. And the thing that struck me the most, I loved the trip, but what was really kind of scary a little bit was we met up with the person who manages the IT, all the computers, and we discovered that basically his job full-time is to be looking on everything online to find computer components from the 1980s, because these nuclear power plants were conceived of in the 1970s and 80s. So by the time that they were conceived, they were put into place and have been in place, the computer system is like a 1980s style computer system, and you can't just change that, right? And so they have to find components that were made in the 1980s for computers. And his job is just basically going around on eBay and Le Bon Coin and all these other websites, trying to find stuff. It's kind of scary, but at the same time, we've never had any accidents in France, and we produce 80% of our energy from nuclear. So it's reassuring, but kind of surrealist to think about that we're running in 2025 on technology from 1980s in the computer parts. Okay. So thank you very much for your presentation. It was very interesting. Clearly, you guys were very much into your topic, and we learned a lot. So thank you very much.
Thank you.
Thank you.
So, that is Physics Bites for this week. We hope that you enjoyed this episode, and we would love to hear what you thought about the topic in the comments section. If you did enjoy the show, then subscribe to our podcast, share it with your friends, and be sure to leave us a 5-star rating on whatever platform you're listening on. And more important than all of that, come back soon for a new episode.